Hi, I'm Alexander Jenkins, a PhD student at Imperial College London, and today I'm going to talk to you about fair and skill diverse student group formation via constrained K-way graph partitioning. Forming groups of students is extremely important in schools and universities. Diversifying skill sets within groups has been shown to create a stimulating and productive environment for learning. But group formation is challenging, and that's partly because we need to satisfy multiple different constraints, for example, constraints on diversity and inclusion and on group sizes. Group formation is also often done manually, and as a result, it's subjective and laborious. In this work, we propose to learn student skill sets from only course mark data in an unsupervised manner using the graph Laplacian eigenmap. And two, we propose to solve skill diverse group formation with constraints using K-way graph partitioning. We demonstrate the effectiveness of our algorithm on a dataset of undergraduate course marks from Imperial College London. To motivate our work, we first need to consider the typical analysis of course marks. So given a dataset of n students and L courses, we can either visualize them as a heat map where the marks per student and per course is visualized, or two, we can either construct and compute two statistics, the average mark per course or the average mark per student. But note that these three different methods for visualizing the dataset don't really tell us much about what skills are present in our data. To do this in our work, we model each student as a vertex embedded in an L-dimensional space, where the position in this space is given by the vector of course marks. We denote this by the vector R. So given students may have some skill sets or preferences for certain courses, then our observed course mark data could be derived from an underlying low-dimensional manifold. So we can learn this manifold using common manifold learning techniques, one of which is the graph Laplacian eigenmap. To construct an eigenmap, we first define a graph, then we construct the graph Laplacian, and then we take the eigen decomposition of the graph Laplacian to yield a matrix of eigenvectors. Then we can represent each vertex, or in our case, each student, in an m-dimensional space, where m is much less than L, and this space we can denote the new positions of each student given by a new spectral vector. So a graph is created whereby each student is defined as a vertex, and then we compute the edge weights in the weighted adjacency matrix as follows. So we use here the correlation between two course mark vectors corresponding to two different students to represent the similarity between the student course marks. So what we have here is a way of computing the weight between two students where we assign a high weight if two students have very similar course marks, or a low, if not zero weight, if they're highly dissimilar. We also have two hyperparameters here, A and B, which we can tune and will influence the low-dimensional embedding we learn for each student. And what do we find? So we do this on our data set, and we find that the spectral vector does indeed encode the student skill sets. So this is shown here by reducing the dimensionality of our space, which was originally L equals 23 course marks, to a three-dimensional spectral vector. We can then visualize students in this new reduced dimensionality space. Here we do so on the left figure, where we plot students using their first two elements of their spectral vector. We can see from this figure that students sort of group into three different groups. We can see the purple students, pink students, and the teal-green students. And then in order to explain this grouping, we plot the mean course mark against each and every course mark available in our data. What we find is as follows. We find three different groups. One, we find to be a below average in mathematics group. And then we find above average in mathematics group. And then lastly, we find another group of students where they perform consistently high across all of the modules. In order to perform fair and skill diverse group formation, we have to define what we mean by fair and skill diverse group formation. So firstly, let's start with a skill diverse group. So from the observation that students with similar skill sets are positioned closer within the eigenmap, where these skill sets correspond to below average, above average in mathematics, and consistently high achievers, then what we can do is compose a skill diverse group as a group made up of students with maximally different spectral vectors, and this corresponds to picking students to form a group where they're very far apart in the eigenmap. In order to do this, we need to measure the similarity between the spectral vectors of each student. We can do this using the Euclidean distance, which we compute using equation 2. So in this work, we've chosen to measure fairness using the balance of a sensitive attribute. The balance essentially compares the ratio of a sensitive attribute in a given group to that of the population. A balance of 1 means that they're in total equality in the population and the group. A balance of 0 means total disparity. So our definition of a fair group is a group that satisfies a constraint on the balance for each sensitive attribute. And this lower bound constraint pushes the value of the balance towards 1, which indicates balance between the group and the population. And as I noted, we solve this problem using graph partitioning. Graph partitioning is a method for clustering graph vertices into different groups. A k-way graph partition denotes k groups. In order to perform graph partitioning, we define the graph partition vector W, which takes values 0 and 1 for each edge present in our data and our graph. Values of 0 represent students which are not grouped together. Values of 1 represent students which will be grouped together in downstream groups. So what we find is as follows. We frame this problem as the following optimization objective. What we do here is formulate the problem as an integer programming problem. What we do is seek to find the values of W, the elements of our graph partition vector, which maximize the following objective here. So the objective on the right hand side, what we have is our values of W, which take value 1 if 2 students are in the same group, times our value of D. And D, remember, is the distance between these two spectral vectors. So by maximizing this objective here, what we're doing is promoting groups to form which are maximally different in their spectral vectors, maximally skill diverse. And then we introduce some constraints. We have the triangle inequalities, which impose restrictions on the groups. So for example, if we have 2 students M and M, which are in the same group, and M and O, which are in the same group, then the students N and O must also be in the same group. We also have a constraint here on the group sizes. To do this, we compute firstly delta here, which indicates the indices of the edges adjacent to a vertex M. And what we have here, FL, is a lower bound on the group size. And then to explain the other terms, what we have is also an upper bound on the group size, but this broader term on the left-hand side, what we have here is so we have the indices of the adjacent vertices, and we apply that to the graph partition vector, and then we compute the sum of this graph, of the subset of the graph partition vector. And this basically just tells us the number of vertices in the same group as the vertex M. And then we also constrain W to have an integer value. And then we also include our fairness constraint here measured with the balance. We introduce a lower bound of the balance, which can take a different value for the different groups depending on the sensitive attribute present. And then we also compute the balance of the sensitive attribute in the group containing the vertex M. You can look at our paper for an exact definition of these values. So using this objective and performing some experiments, we used 10 students chosen at random from our Laplacian eigenmap and our data set in order to test our algorithm. And then we constrain our groups to be the same size. We want them to be of size 5. On the left-hand side here, what we do is minimize the objective on the previous screen. What we see is that as a result, students with similar skill sets, shown with similar colours, are put into the same groups. In B, the middle figure, what we have is students, we've maximised the objective on the previous screen, and what we see is that students represented by different colours are now in the same groups. This represents skill diverse groups. Figure C shows our optimization objective where we maximise for skill diversity, and now we introduce a fairness constraint. So here, the students with a sensitive attribute are denoted by triangles, and we pick these students such that their skill sets are the same. So what we see here is that the previous two methods, without this constraint on balance, the triangles appeared in the same groups. And the third groups in figure C, they appear in different groups. So we're able to constrain and promote fairness and skill diversity in our objective. In order to validate our method, what we've done is plot the correlation of marks within each group under each of these different circumstances. We can see that when we minimize our objective, we promote similar skills within each group, and this is given by a high correlation of marks within each group. Figure B, we promote skill diversity, which is a low correlation of marks within each group. And C, we promote skill diversity and fairness, where we can see that the skill diversity is retained when we introduce this additional constraint. So in summary, we've proposed a method to learn student skill sets from course mark data in an unsupervised manner. And two, we've proposed an objective, an optimization objective, to solve skill diverse group formation with constraints using k-way graph partitioning. Finding the optimal solution with graph partitioning is an NP-hard problem, but to scale to larger data sets, we can use heuristic solvers. We've actually deployed our algorithm to assign undergraduate students into tutorial groups this academic in the EEE department. In future work, we will detail our findings. So thanks for listening, and thank you very much to my funding bodies and collaborators.